So I'm going to continue on the topic of artificial neural net from where we stopped last time. And last time I think is introduced the concept what the ANN, artificial neural net, is, and starting from like a perceptron, and like here from perceptron to multi-layer perceptron. This multi-layer perceptron is I would say identical with the artificial neural net. There are many ways that we can explain it, and there are many ways that we is looking at the multi-layer perceptron. But in my lectures, I mentioned two perspectives. First one is let's see. Let me see, where is it? It's for nonlinear classifications. It's corners. Corners. Usually we have to define the corners, but for ANN is they're trying to find the corners from the data set. And the second perspective is that linear boundaries. So usually for nonlinear classifications, it will be curved for classification boundaries, and we can approximate them as a piecewise of linear. Okay, that's why we have, where is it? We're gonna have multi-neurons in the single layers. So those are two ways looking at here. Like I said, there are two ways of looking at the artificial neural networks. And here is weight, gonna represent the linear classification boundaries. And another way is that it's a nonlinear relationship between the input and outputs, or nonlinear mappings. Here, this one is kind of, you might think this one as a universal function approximator, and this one is kind of universal function classifier. Here, let me see. You guys can, in conceptual way, you guys can think from inputs, basically is trying to get good features. We call it feature learnings or feature extractions from the data. And the later part of that is linear classifiers. It's combine them together. But the thing is that weights, we learned the weights simultaneously, right? So in the machine learnings, we define the corners to define the right features by users. First step, that was first step. And the second step is based on here features we define, not like linear classifiers, but here in ANN we're gonna find the omegas at the same time. And if you put more layers on it, we call it deep artificial neural net or deep learnings. So it's have some kind of higher capability of finding a good features. I think that. And those are like a conceptual explanation of ANN. And the next step is, of course, here a lot of omegas, weights and bias. And of course, we have to think how to find those omegas. We call it how to learn the models from the data set, how to train the models from the data set. So I never explain it. So now it's the right time to thinking about or talking about how to find omegas and bias. So those gonna be the main topics for today. So so it's training, find omegas and B's. like I said, I mentioned so many times that we can think of machine learning as optimization problems. We're gonna follow the same procedures. So training neural nets is find the omegas. I'm gonna transform all the things into the optimization problems. Learning or estimating weights and bias of multi-layer perceptron from training data set. Okay? That's what we're gonna do. And I'm gonna explain the fundamental things a conceptual way, but later on, the thing is we're gonna use a Python. So actually we don't have to, we have to know, we have to understand like how do you learn or estimating weights and bias from the data set. It's really important, but when it comes to implementing, actually you don't have to understand it, because we're gonna ask Python to do that for us, right? So optimization, if you remember, there are three key components in it, like objective functions and decision variables, unknowns and constraint. Those are three key components in optimization problems. And we can have mathematical expressions for optimizations like here. Okay. We're gonna minimize something by changing omegas. Here, omega is all the omegas in neural net. Okay, omega and bias, I'm gonna just say omegas, right? So in right way is the omega is bias, but I'm gonna say just omegas. So omega is decision variables, and I want to minimize something. So I'm gonna show, here is objective function is f, but okay. So I'm gonna tell you later on what's gonna be the objective functions in neural net. And one thing that I want to hear is that neural net is like this kind of structures, right? And all the omegas. So it's a parameterized. It's a parameterized. That's why we are able to define all the decision variables. It's parameterized. Right? So in optimization, we call it objective functions. But in same thing in ANN, we said it's gonna be loss. It's gonna say loss functions are the same. So if you think about loss, I want to minimize loss, right? So in here is already it's gonna be the minimization problems. So instead of I'm saying that I want to minimize objective functions, I'm gonna say minimize loss functions. Same as objective functions, same as, right? So the loss function is gonna be the target values and predictions. I wanna measure the errors between them, and then I'm gonna control or adjust the omegas such that minimize those discrepancies. Right? Again, it's a part of this. I'm assuming that it's part of the supervised learnings. So this for X is input and Y is outputs or corresponding to labels. And these, what it is, this is the predictive values from ANN, having the input of X. So it will be like, so it's gonna be X and the Y hat, same as I'm gonna say it's functions of X parameterized with omegas. That's kind of notations. And I didn't define what the loss function is, but says some kind of loss between these two terms. And since we have many data, say suppose we have n data points, I want to minimize them. That's kind of generic expressions for neural nets. So again, let me summarize it. We can think of it as optimization problems, and objective function is same as loss functions, because always we're going to minimize the errors between the target values, which is true labels, is going to be given for supervised learning problems, and prediction is the predicted values out of. Okay, of course, we're gonna use the computers to find out the right values of or estimate the omegas. So that means I mentioned so many times we're gonna use iterative way. So at the beginning, we're gonna randomly initialize the value of omegas. So here is estimated value is gonna be way different from true values. Why? But how much these two values are different? Using that information, we're gonna update it omegas. Somehow, I guess most of you guys already know what it is. How do you update the omegas? I'm going to talk about it in a minute. So using that kind of iterations, the omega is gonna gets better and better, such that to minimize the loss functions that I'm going to define it. All right? So that's, and here is omega, loss functions. It's really up to you. You have to define the loss functions for your own applications or your own problems. That's okay. But let's see this one of them examples here. For regression problems, looks familiar, square the loss. For classification problems, cross entropy. You guys remember, we already learned, it's like from logistic regressions, when we talk about the logistic regressions, cross entropies for classification problems and the regression problems. So by having different definition of loss functions, it could be regression problems or it could be the classification problems. That's why ANN can work as a regressor or classifiers. It really depends on how you define your loss function. And the next thing is how do you update the omegas? There are many ways probably, but the only thing that we learned is that gradient descent. Here we're gonna use a gradient descent to update the omegas, even in the neural net. Right? That's why I think in the machine learnings, I think I introduced the concept of gradient descent, because we know that we're gonna use the same thing in here in artificial neural net or even for deep learnings. So it's gradient descent is the way that to update it. How do you update it omegas? Starting from the original omegas here. And this is loss functions or objective functions. And we have to find a gradient with respect to omegas. Don't worry about how to compute it. Don't worry about it. But these are the objective functions, the loss functions, and gradient. And with respect to omegas, because omega is that's something that we want to update it. And alpha is step size or learning rate. And remember, it's minus because we want to do gradient descent because it's minimized, because it's a minimization problem. So it's negative gradient points directly downhill of the cost function, or I will say loss functions. And we can decrease the loss or cost by moving in the direction of negative gradient. Alpha is running rate. I think you guys all know. I mean, that's it. That's it. I mean, of course, we have more things to say, but that's good enough. Gradients in ANN. To find all the weights and bias from the data, we're gonna use a gradient descent. Basically, that's what I said. But there are some technical issues. There are some issues on that. What kind of issues that we have? Let me show you. Say we have this kind of networks, and we define some kind of loss, and we have omega 1, omega 2. I mean, okay, let me add. So we have 3 neurons and 4 and 2. How many weights in between the first, input and hidden layers? How many weights? Anybody? How many weights between the input layer and the hidden layer? We have, let me see, 12 omegas, right? And more specifically, we have how many? We have to include 4 bias as well, but I'm gonna skip this. And here we have 8 omegas between hidden layer and output layer. So in total, probably we have 20 omegas. And actually here is 2 B's. So actually we have 6 B's as well. But you can say 26 unknowns or 20 unknowns. It doesn't matter too much, but at least you got the point. So we have 20 omegas. That means in the loss functions, we have, in order to compute the gradient, we have to compute for each omegas. Suppose I would say it's 20, that means in order to do 1 iteration, for each iteration, we have to compute these partial derivatives 20 times. But if we have like, say 100 or 20, like 150 and like 10, imagine how many omegas and bias. There are too many computations are required for all omegas. That's the technical issues. In theory, doesn't care. It doesn't matter. In theory, we're just gonna say, I'm gonna use a gradient descent to find out omegas. That's it. But when you implement it, think about it. How many like computations or partial derivatives are required for each? For each iteration, we have to do like multiple or many iterations. So that's kind of technical issues for like when applying the gradient descent into the artificial neural net to find out to estimate all the omegas and bias. So there are some smarter way that we can do. So if you think about the structure of neural net, there are some specific structures. What kind of structure that we have is input layers, and we have neurons, and we have following layers, another neurons, and things like that. So it's a So here, these you can think of as a functions, right? Linear mappings, right? So it's a composition of functions. That's very specific structure, the specific characteristic of the neural net, because we have this kind of structures. Because we have multi-layer MLP, right? And for derivatives, since you have a composition of functions, we can apply chain rules. Chain rules. Those are very like the characteristics of this is from the fact that it's from the structure constraint. And dynamic programming is I'm gonna explain it in a following slide. So thing is that, I mean, we have to do this, we have to do this, we have to do that, but we have to utilize the specific characteristic of artificial neural net. That's the idea. That's the idea. To reduce some kind of burden of too many computations. Okay, so before I mean, let's say it's machine learnings and versus deep learnings. And it refers to ability to AI refers to the ability of machines to mimic human intelligence without explicit programming. I mean, that's kind of the formal definition of AI. And here in the machine learnings, if that's, for example, if that's the nonlinear classification problems, we have to define, we as a users, we have to define what kind of kernel that I'm going to use, hoping that over here, the feature is linearly separable. So it's really critical. How do you find right kernels? Same as how do you find the good features, we call it feature engineering. On the other side, deep learning is feature learnings. We want to find omegas. That means over there is working as kernels. But instead of me defining, gonna ask deep learning models to find the right features for us from data set. Right? So finding omegas is really important. It's really important. Finding omegas here is equivalent to, I'm gonna say this, finding right kernels. Finding omegas over there, equivalent to, I'm gonna say, finding right linear classifiers. Right? So keep those things in your mind and hold it. I'm gonna explain what dynamic programming is, and I'm coming back to the how do you find the omegas, right? So dynamic programming is probably more, I think like most of you is like the first, never heard of it. So I'm gonna explain what dynamic programming is, because we need that to find the right, to find the omegas and bias. So recursive means that, so okay, so this one is like, has nothing to do with all the materials that we learned so far. It's totally different topics. So I'm gonna just move these topics to explain dynamic programs. I'm gonna come back, right? So one of the central ideas of computer science, and it depends on the solutions to smaller instances of the same problems. I'm gonna say sub-problems. Functions to call itself is impossible in the real world. And up to this point, you guys have, I guess you guys have no idea what I'm talking. One of the famous examples of recursive is factorial. So how do you find 6 factorial? Is that, I mean, this is the definition, right? This is the definition of factorial. And this one is, right, we can write it this way. Functions, if the function is compute the factorials, in order to compute this, we have to call this guy. But this one is smaller or solve problems from 6 to 5. And 5 factorial is same as 5 and 4 factorials. Okay, that's why we call it recursive. It's recursive. Okay. So for illustrations like that, if you have like some kind of functions, or you want to define it, and the inputs, in order to compute the outputs, we have to call it smaller. And in order to compute this guy, we have to do and even smaller. Just repeat the recursive. And going down to down, eventually this is 1 factorial, right? And at the end, if do not have any kind of stopping criteria, have an infinite loop. So in general, we call it is base case, like this one. So if that's the base case, the output's gonna be like that. And if not, we're gonna do recursive. That's typical way of recursive. I'm gonna explain with the examples, I guess. I mean, it looks difficult, but you guys already know. And we call this dynamic programming. Is again, another the most famous example of dynamic programming or recursive is Fibonacci numbers. The definition is like that. So the first and second is equal to 1 is defined. And we have this kind of relationship. Let's say we can compute it like this one is same as by definitions, and we already know it's 2. And we can compute this guy because like that by definitions, we have 2 plus 1, things like that. We can compute all the Fibonacci numbers. You can compute it. Right? And let's compute the Fibonacci numbers using recursive way. What we can do is that if you remember this one is what would be the base case? Here is base case is when f, right? So when n either 1 or 2, the f is the output is equal to 1. Otherwise, we have to compute like this. Otherwise, we have to compute. And so this is base case, and these are the recursive. To compute this guy, we have the same functions inside. In order to let me repeat that. Compute this, we have smaller problems inside. It's recursive. Have another smaller problems inside. That's recursive algorithm. And it works. So let me ask, do you think it's good or not? In terms of computational efficiency. Do you think it's good or not? Let me show you this guy. Suppose we have to compute that. And in order to compute that, we have to compute these two. In order to compute this, we have to compute these two. In order to compute this, we have to compute these two, right? No, it's good. That's, I mean, basically it's the definition of recursive. But the issue is that here, to compute this guy, we have to compute that. We have to do computations. But here, we have to compute that again. So it's repeated. It's unnecessary. I'm saying it works, but it's not efficient. It's not good. It's not good because it requires repeated computations. Right? So is there any suggestions to improve that? To reduce the computational cost? Any ideas? Those are the issue of naive recursive. So let me suggest enhanced, more better way. Say, whenever you do the Fibonacci computations, after you're done with the computations, we memorize it. We remember that values. We memorize it. And later on, when it's like the value is asked to compute it, actually before we do the computations, we're gonna see whether it's already computed or not in your memories. When the value is already computed, you don't have to repeat. We don't have to compute it again. Just get the values from your memories. And if you cannot find it, that means that you do this computation at the first time, then you have to do it. So it's a better way is that assign some kind of memos or memories. And if n is in memo, that means you already did that. Did computations. Then actually you don't have to compute it. In that case, return the values from your memories. If not, then repeat the do computations in the recursive way. Okay, when you're done, put that values in your memories. Later on, we can use that. This one is better than naive. Right? It's too obvious, right? So the benefit of this memorized is that it's only recursive the first time it's called. All right? So let me show you starting from here, we have to compute this guy and this guy. And I don't know whether we do this one first or then if you compute this one, put in memories, and later on, we already did that. So we're not gonna do, we're just gonna get the values from the memories. Then you don't have to do the computations. So we can reduce tremendous amount of computations. So it's way better, way smarter. So we call it memorized recursive algorithm. This one, we call it dynamic programming. don't worry about the namings. Why is dynamic programming is related to memorized recursive? Don't worry about the names. This DP is memorized or remember and reuse the solutions to solve problems. So that's the dynamic programming. All right. Using that conceptual understanding of DP in your mind, let's move back to the original problems that we talked about. How do you find the omegas and bias in the neural net? So the name is that it's back propagations. And again, I'm going to explain it. So don't worry about what the back propagation is. Forget about it. You don't need to know. And later on, I will explain it. So let's come back to the issues that we had in the gradient descent in ANN. Is that we have to find the weights and bias from the data using the gradient descent. The issue is, I mean, theoretically, it's totally fine. But the one is that if you have so many weights and bias, then that means we have so many computations to compute the partial derivatives with respect to all the omegas. So the answer is that we're going to use dynamic programming. Dynamic programming. How? Let's see. There are two. The first one is forward propagations, and the second thing is back propagations. So suppose we have any kind of networks, and the omega, suppose the omega is given. It doesn't matter whether the omega is the value is like good or not. It doesn't matter. If you have any kind of omegas, that means we can do new inputs x. We can compute it. What kind of computation do we have? Over there is matrix multiplications. And each neurons, if that's a sigmoid nonlinear activation functions, we just have the nonlinear mappings and we repeat matrix multiplications and nonlinear functions going through and repeat that because we have multi-layers. So that's the forward propagations. If we have some kind of values on omegas and the bias. Okay, so it says information propagates up to hidden units at each layer finally produce the outputs. On the other hand, back propagation is that in order to compute the gradients, we're gonna do this way. We're gonna do this way because we have loss. Okay, say we have some kind of weights over there. Say it's K, and over there is weights like say S. Then there are many, but see over there we have to compute omega K. Over there we have to, for this guy, we have to compute omega S. I mean, we have to compute all of them, but there is the good reasons that we do the back propagations related to dynamic programming. At this moment, probably you guys don't understand what I'm talking about. In the following slides, I will show you. Have a lot of benefits having compute the gradient in backward in these directions. It's related to dynamic programming. It's related to memorize. So for that, let me explain it with simpler example or simpler case. So far, I think like this is the way that I draw, but here in that directions, say this is the input and this is the output in a vertical way. And the simplest network you can think of as like that. I mean, simplest way, okay? And the function is gonna be different, like say f of 1, f of 2, f of 3, and f of 4, in order to make simple, like to say it's all the functions are the same, and just for explanations. Okay, in that, let me see, we have the value of u and omegas and x and y, and the output is z. Now I want to find out all the z is like same as in the loss functions. And what I need to do, I need to find that guy, and I need to find this guy. I need to find these gradient to find out in the next iterations whether we're gonna update for y, x, omega, u. I have to decide it in the next iteration whether I'm gonna increase and decrease. It really depends on the value of these derivatives, gradient, right? We have to compute it so then we can decide in the next iterations. In the next iterations, whether we update like increase and decrease for each decision variables. In this case, it's y, x, omega, u, which is weights. Now, say, I mean, we have to compute all of them. And then let's see. Let's find out this one first. This one we have to compute it. And what about x? We have to compute. In order to compute this, we know that z is f of y, and we know that y is f of x. Then we can. This is why. Why is that? Because it's a multi-layer perceptron. It's compositional functions, and then we can apply chain rules. So what kind of chain rules like that? Right? This one is same as f prime. Then thing is that in order to compute these derivatives, actually we have to compute this one and this one. Omegas, we have to compute, it's chain rules. Z is a function of y is a function of x is a function of omegas. In order to compute this derivative, we have to compute this guy and this guy and this guy. Okay, let me repeat that again. U is function of y is function of x is function of omegas, omega is function of u. Okay, if you in forward directions to compute the gradient, then we have to compute this one first. In order to compute this guy, we need these derivatives and multiplications because it's chain rules. But let's say I want to compute the gradient in backwards, in the other way. Then we're going to compute this one first. We have to compute this guy. And this one, to compute this guy, we have to compute these two. But remember, like in dynamic programming, is memorized and recursive, we already compute this guy from, then we don't have to compute it again. Just get the values from your memory. The only thing that you need is you need to compute these derivatives. And then put the values in your memories. And next thing is I want to compute this guy, and I do have these two in my memory. I don't have to I don't have to repeat the computations. Only thing is that get these values from memories and compute this one. What about that? I already did that. And this actually we need that. So that's why if you compute the gradient in backwards, compute it and put the in your memories. And the next thing is that you compute and you get the values from memories and do the computations. Exactly, it's the same as dynamic programming or memorized recursive. That's why we call it back propagations. Back propagations. That's the key idea of gradient descent in neural net, artificial neural networks. Okay? So we can update weights recursively with the memories. So I guess it's good enough to understand what back propagation is. So I'll give animations like that. So it's now it's with the memories. So basically, in summaries, this is how they trained. It's optimization problems, and we're gonna use the gradient descent, and to make it more efficient, it's back propagations. Memorize recursive with the memories. And it's not, I mean, we can implement it, but it's not easy to compute all the gradient in general. The good thing about it is that all like many previous researchers already done all the hard works on developing numerical solvers or libraries. So there are a wide range of tools. We're gonna use Python. Right? We're gonna use a Python. So core review of foundation reviews is we're starting from the perceptron and extended the concept into the neural networks, and how you train it. We can use like numerical libraries, things like for example, Python, things like that. So next thing is that, again, is in the scikit-learns. I think I mentioned many times in the machine learning problems, we can use scikit-learns as embedded functions. Same thing we can do. We can, for artificial neural net, there is some embedded functions or libraries or modules in the scikit-learns. So we can use that to find all the omegas. So one of the famous examples is MNIST data set. And probably like this is most of them is not the first time see the word MNIST. MNIST is Mixed National Institute of Standard and Technology Database. Basically, in the post office, you say it's a lot of written digits. We call it handwritten digit database. So basically, you're gonna have this kind of inputs as an image. And it's I'm gonna make it as a classification problems. What kind of classification? Having that as an input, I'm gonna say 5 and 0s and 4, 1. I mean, as a human being, it's not that difficult, But imagine like you want to make some kind of computer or AI models to classify or to estimate it, right? Digits from the handwritten digit images. So we're gonna use the ANN. I think you have these kind of things in your previous homework assignment. So I guess you guys already know what kind of it's a 28 by 28 grayscale images, and you can think of it as a 28 by 28 matrix. And since I never taught how do you handle the images as inputs, the only thing I think that we learn is that it's the column vectors. So we have to flatten. So make it a vector. So it's 28 times 28. So it's a 784 column vector. So from 28 by 28 images like this, I'm gonna transform it like that. Having this one as inputs, having this is gonna be the inputs, and ANN models to estimate it, the digit. So this is multi-class classification problems, right? I think it's okay. And the input number of neurons, it's 784 because it's a column, it's a vectorized columns. And number of hidden layers, that's really, this kind of, it's a structured design. It really depends on us or depends on you. How many hidden layers that we're gonna have, or for each layers, how many neurons that we're gonna put, it really depends on you. And in these lectures, I'm not sure whether this network is the optimized or not, but it doesn't. I'm just gonna have, say, I'm gonna have one hidden layers with 100 neurons. Of course, that's not the optimized one. I'm just show you one of the example of that. And the output, since we have from 0 to 1, I mean 0 to 9, so it's 10 classes. So that's why we have 10 output. In the output layers, we have 10 neurons. 10 neurons. So that's the structure that I designed. The next thing is that we're going to have many input and true labels from this data set, showing them. That means each have omegas. Using back propagations, we're going to update it, omegas. We're going to update the omegas. Once we're done with the training, or once we're done with the learnings, once we're done with optimizations, all the omegas and new inputs, we're going to do 4 propagations to estimate y hat, hoping that this is close to with true values. We call it inference, or we call it evaluations. So it's a 2-step training, and later when we're done with the trainings, we're gonna have the models. Using that models, we'll do evaluations, or we'll do inference. Right? For specific this kind of structures, and counted how many omegas here, over there, that's the number of, that's the number of nuns. I did not include the bias. With bias, we have 100, bias with 10. Those are total number of unknowns or decision variables. Then you can get some ideas like how many, like the complexity of optimization problems. These are the total number of unknowns, not the data set. These are total number of unknowns. We have to estimate all the unknowns. we're gonna use back propagation, or I'm gonna say we're gonna use a gradient descent. Right? And imagine you have to see like always whenever you design the networks like this, you have to think about how many unknowns that you're gonna have in these models and relate it to like the complexity of your models. Remember, like overfitting problems, if you do not have enough data set, and in that case, it's like tends to have overfitting problems, right? Smaller data set with many unknowns. So always you have to be careful. Be careful. It's like extremely easy that it will get like the overfitted because of this kind of reasons. So it's iterative optimization problems. And with X, the neural nets gonna have 4 propagations. We do estimated, we make comparison with the true values. Of course, at the early stage of the training process, the loss is gonna be large. And based on these loss functions, we have to do gradient descent update. We're gonna use some kind of optimizers and updated omegas and repeat that process. So in scikit-learns, and here, let me see, in the sklearns and neural net, it's multi-layer perceptron classifiers and have MNIST data set. And this, we have to design it. So we draw these networks and hidden layer size, we have 100. What kind of linearity functions? I'm gonna use the logistics and solvers and running rate and batch size and like maximum number of iterations and things like that. These are, it's not, batch size means that each iterations, how many, so the data points that we're gonna use instead of one or instead of entire data set. So sometimes it's good to assign the batch size. And again, the fit. Train X, train Y, and do iterations. As you can see, the loss is gonna get smaller and smaller. And once we're done with the training process, next thing is that we either test or evaluate it with test data set. And with the accuracy score is test data set, we have predictive values, and it selects 96% or accuracy. That means in the testing data set, like you misclassified like 4 out of 100 data points, right? So this is like predictive values. And I think I did not explain why we need at the end, why I need like 10 neurons. So each neurons have sigmoid functions. That means from 0 to 1 and 0 to 1. You can interpret as, if this is zeros, then means that the input is what kind of probability that this input is classified 0. And here if we have some kind of values over here, that's gonna tell us that what kind of probability that the current input is the probability that belongs to class 1. So that's why we have 10 digits. 10 neurons at the end. So for each probability is like this. So having this one is inputs, we say like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have highest probabilities that this one is network is gonna tell us that like 7. So I have to pick over there. Let me see. This argmax. because we have to pick the maximum argument, right? So that's all we have. And I'm going to show you. So actually, I'm going to run let me show you. So this one is a notebook related to training the ANN models, and the same thing that I just had here. Let's see, you have to download all the MNIST data set. And actually this is as you can see here is 28 by 28. So everything is flattened out, is a factorized column. So it's a 784. Those are the number of training data set. The output is one hot encoded. So we have 10 neurons. And here the test data set, we have, these are the number of training data set. These are the number of test data set. So as you can see, I said it's a gray scaled images. You can think of it as a matrix. And these are the shapes, columnized. The images, shapes, and 28. Whenever you plot it, we have to reshape it to 28 by 28. So this is the image, like one of the images in the MNIST data set. And I think it's one hot, I explained what hot encodings. So it's labeled is one hot encoded, like that. Since this is one, the first digit is the class is 0 and class is 1. That's why we have all zeros except this one. And the argmax 0, 1. That's why Python is starting from the zeros, right? So it's that's how we predict out of this. And again, we need MLP classifiers from the scikit-learns. And this is the shape, and print out. And we defined the structures and what kind of activation functions, what kind of solvers that we're going to use, and what's the running rate and batch size, things like that. And that's we run actually now is training. As you can see, the losses get smaller and smaller. Okay, and after that, we're done with that. Now I just said 20 times, 20 iterations, probably you can change the values like 100 and really see what kind of effect that you're going to have. So these are the prediction accuracy. It's like almost like 28. The evaluations, let me see, this is the 1, and actually this is the right predictions out of it. Let me see, 5 to 5. Get test data set 100. Let me change. All of them are 1 or not? Let me see. Oh, here we have to change it. So let me see. You can test 1 and show. Predicted 1. Okay, so you can over there. You can change from the test data set. I think you have to change this one, and I'm not sure whether we got the errors, but you guys can. I'm not. So this, right? I'm showing. Okay, so probably I don't think about it. How do you evaluate and predict and plot the values, different data points in the test data set, right? So that's all I have for ANN. So let me summarize this one. So starting from the machine learnings, and this is the last topics, is kind of at the beginning of deep learnings. right? So you always remember this title is from the perceptron to multi-layer perceptron, or I would say from machine learnings to deep learnings. And I think it's conceptual wise, I think I explained it enough. And actually, and what I explained it today is how to find the omegas from the data set. And here, the example that I have is that we use scikit-learns, but actually in many cases in deep learnings, we're gonna use a TensorFlow, which I'm not gonna cover in this semester. But I think it's for the advanced learners or students, probably you can Google it to see. We have tons of study materials out there, all right? So I'm going to stop here.